Welcome to our lecture session. In this video, we will discuss the properties of limits or the list of discovered and established facts about limits. In mathematics, properties is a collection of what is true or what have been proven to be true about limit. So, every statement in the form of theorem that we will mention are claims whose proofs exist and can be seen in many mathematical analysis books. I said this in advance because this lecture series is not really intended to discuss the proofs of the claims. Instead, we plan to enumerate mathematical properties and see how we can utilize them. This discussion is important as it simplifies the process of finding limits of functions. Imagine having a set of tools at your disposal, allowing you to determine the limits with ease and confidence. So, without further ado, let us let me kick this off with a very important property that says that the limit of a function, if it exists, is unique. Yes, a function can only have either no limit or exactly one limit at a given point. Hence, we are now at the liberty to use the phrase the limit because such a thing is unique. If you're interested to see the elegant proof of this theorem, you can check the book of Bartel and Sherbert entitled Introduction to Real Analysis. With that said, let us start the journey of finding the limit of a function using analytic approach. To start the journey of finding the limit of a function using analytical approach, the following basic limits will set the foundation. Let A and C be real numbers. Then, first, the limit of A as x approaches C is still A. This means that the limit of any constant is that same constant no matter where x goes. Illustration, the limit of 5 as x approaches 7 is still 5. The limit of 7 as x approaches whatever is 7. Limit of pi as x approaches whatever is pi. And so on and so forth. Second, the limit of x as x approaches c is c. Examples, the limit of x as x approaches 7 is 7. The limit of x as x approaches 1 is 1. The limit of x as x approaches e is e. And so on and so forth. So there are now two functions, namely the constant function or families of function. So the first is the constant function, and the other one is the identity function that whose limits are known to us. But of course, we will not be content with it, just these two. We want to know the limit of other functions such as a combination of variables and constant, the combination of these two, using algebraic operations so like addition, subtraction, multiplication, and division of functions. So to do that, we need to know how algebraic operations affect the limit of a function. So the following list of properties will how uh, reveal what is the answer to this. All right. So let us recall that the basic limit properties allows us to find the limit of only two types of functions: the constant function and the identity functions. And we wanted to expand this list. And one way to do this is by combining functions through algebraic operations of functions. So we need to know how the limit operation interact with these operations. What properties does it carry? So here's the theorem. So let A and C be real numbers, and if f and g are functions whose limit exists at C, then for addition of functions, we have this. Very much expected, right? So it says that the limit of f of x plus g of x at C is equal to the limit of f of x at C plus the limit of g of x at C. Alright, so it's kind of saying that the limit of the sum is just the sum of the limits. With regards to subtraction of function, the limit of f of x minus g of x as x approaches C is just equal to their individual limits. Limit of f of x at C minus limit of g of x at C. In other words, the limit of the difference of these two functions is just the difference of these two functions at C. For multiplication, the same. The limit of f of x times g of x at C is equal to the limit of f of x at C times the limit of g of x at C. In other words, the limit of a product is the product of the limits. Lastly, the limit of f of x divided by g of x is equal to the limit of f of x at C divided by the limit of g of x at C. Put differently, the limit of quotient is just the quotient of the limits. Provided, of course, that the limit of g of x, this function down here, exists and is not equal to 0. Alright? So those are important assumptions, as well as this one, that f and g are functions whose limit already exists at C before we can perform this maneuver. We can separate the sum, we can separate the difference, the product, and the quotient of functions under limit. Okay. Other properties of limit in relation to algebraic operations are scalar multiple and exponentiation. These properties are simply the consequences of the previous ones. So let a and c be real numbers and m be a positive integer. If f is a function whose limit exists at C, then for scalar multiplication, the limit at C of a function multiplied by a constant, say a, is the same as a times the limit of the function of that function at C. So you see here that a constant can freely pass through a limit operation. You can set aside a constant. All right. So for properties involving exponents, we have the limit at c of f of x raised to m equals the limit at c of f of x, then we raised it to m. So we take the limit first at c before raising it to m. So those two are similar operations or similar approaches. You can either first raise the function to the exponent before taking the limit, or take the limit first at c, then raise the answer to m. All right. About the proof, well, here is one of the proof from Bartel. Looks scary, right? It is indeed scary, but let us not talk about it for now. Instead, let us discuss how we can apply the properties. Okay, before we start solving the limit problems, it would be useful to have the list of properties by our side. So let us place it there. All right, let's do it. First, limit of x plus 2 as x approaches 0. Um, Remember, at this point, we already have the properties of limit of combining constants and the identity function using those algebraic operations. We have addition, subtraction, uh, multiplication, uh, quotient, scalar multiplication, and exponent. Now, these functions are just a combination of identity and the constant function using these algebraic operations. So we should be able to solve them. So first is to rewrite this into pieces. All right, so we separated them under addition, and now this looks familiar. It is the same as this, and this one looks familiar too. This is the same as that. So we can use the basic limit properties to uh, rewrite this as 0, and this becomes 2. So we have 0 plus 2 equals 2. Okay, so that's our final answer. Number 2, limit of 6 times x squared minus 4x plus 1 as x approaches 2. We first use the, what do we use first? Well, we can use the subtraction and addition property first. To separate the limits. So there are three limits that we want to separate. And now we want to set aside the constant, this one. So we can use the scalar multiplication as well as exponentiation if you want, because there is an exponent here of x. So first is scalar multiplication, then exponentiation. And then already we know what to do with this, what to do with that, and that one using just these two limit properties. Here it is. Right, so limit of x as x approaches 2 is 2. Limit of x as x approaches 2 is 2. And the limit of 1 as x approaches 2 is 1. Simplifying that, we get 70. Very easy, right? Example 3, the limit of 3 times the quantity x plus 2 squared all over x minus 1 as x approaches negative 1. Before we solve this, notice that this is a rational function. That means there is, of course, a fraction and its denominator consists of variables. As such, we need to make sure that the limit of the function in the denominator as x approaches negative 1 will not result to 0. Only then can we proceed with our solution. So let's see. So what is limit of x minus 1 as x approaches negative 1? That will be negative 2. So no problem with the denominator. So we can proceed with the solution. First, what do we do first? Use the division or quotient property. So we can rewrite it this way first. Then, of course, the sum and the difference. As well as the scalar multiplication rule. So now here is we want to use exponentiation property, and then the addition and subtraction property. Okay, so already all of these limits are in one of these basic limits in the form of one of these. So we can use that to get, so our final answer is negative 3 halves. Number 4, another example is a limit of, um, this is a little bit complex function. So it consists of 2x plus 1 raised to 3 multiplied to quantity 7x squared plus 2 all over x cubed minus 2x plus 1 as x approaches negative 1. So just like the process that we did before, we use the quotient rule or the quotient property, division, and multiplication as well. You can do them simultaneously. Then exponentiation in here. Now we use the addition and subtraction property to separate the limits. So here we use the scalar multiple property. Now we use the basic limits, and after we simplify, we get the final result. So the next set of properties is a beautiful one. I'm sure you will like it because uh, This will confirm the conjecture that you may have suspected since the beginning of our discussion in finding limit of a function. Yes, we can evaluate the limit of some functions using direct substitution. Well, the limit of the function at C and the evaluation of function at C are generally not the same. There are some functions that are exempted to this. For instance, the polynomial and rational function under some restrictions. But first, let us recall what is polynomial function. So that is a polynomial function, anything that can be rewritten or that can be expressed in this way: a sub n times x raised to n plus a sub n minus 1 times x raised to n minus 1, and so on and so forth, plus a1 times x plus a sub 0. Here, a sub i's are constants. So these are constants. Okay, and what else? The leading coefficient, of course, should not be equal to 0. And n is a non-negative integers. Whereas our rational function is simply the ratio of the any two polynomials, with the denominator, of course, not equal to 0. All right, so on to the property. It states that if f is a polynomial function and c is a real number, then the limit of f of x as x approaches c is just f of c. Very nice. So we call that process as a direct substitution, because what we really did is just we substitute c in place of x. Okay. The same is true for rational functions. So with just a small exemption, this is the exemption. Anyway, if g is a rational function given by g of x equals h of x over I of x, and c is a real number such that evaluating it at c will not result to 0, then the limit of g of x as x approaches c, we simply plug in c. Okay, so let's do some example. Find the limit of f of x equals x raised to 4 minus 4x cubed plus 6x squared minus 4x plus 1 at x equals negative 2. Solution. Because the given function is a polynomial function, this is a polynomial function, we can use the property that says that we can just directly substitute c in place of x. So we just solve for f of negative 2, and that is an easy task for us, right? Since algebra, piece of cake. Okay. Illustration 2. Find the limit of um, x raised to 4 plus 6x squared plus 3x plus 4 all over x plus 2 at c equals 0. Solution. Because this function is rational, right? This is a ratio of two polynomials. We first need to make sure that the value of c will not make the denominator equal to 0, because we have that condition that we first need to met. So yeah, and indeed this is not equal to 0. All right, so we are now ready to use this nice property of directly substituting c in place of x. And very easily, when we substitute 0 in place of x, we arrive at our final answer equals to another piece of delicious cake, right? So, what a nice property, isn't it? Uh, this is a relief that we can simply directly substitute the c value in place of x. We can simply plug in. Of course, this is not true for all the functions. Luckily, we have polynomial and rational function which allow this direct substitution method, right? Okay, remember the previous examples that we solved earlier that involve too many steps, so many steps. Now we will be able to get rid with most of them. Look at this. All right. So the solution has been reduced to just 1, 2, 3 steps, and here 1, 2 steps. So isn't that awesome?
Awesome.
Aside from the polynomial and rational functions, there are a lot more functions that allow direct substitution when finding the limit at a point. Some of these are functions involving radicals and trigonometric expressions. So, let n be a positive integer. The following limit is valid for all c if n is odd and is valid for when c is bigger than 0 or positive. If n is even, okay, so there is a restriction if n is even. If n is odd, then whatever c is. So we just use direct substitution. Okay, so replace c x by c. All right, so examples. Great. Now further explanation is needed, I guess. So we simply directly substitute. While this property is of some use, it is still relatively little in scope. So we want to find the limit of a more general functions involving radicals. So the next theorem will greatly expand our ability to solve a limit. Look at this. The limit of composition of functions. This is a rather unfamiliar operation of functions, but this is just the same as evaluating a function at another function or a function inside another function. That's a composition of function. So the property says that if f and g are functions such that the limit of g of x at c is equal to L, and the limit of f of x as x approaches L is f of L, then the limit of the composition of functions f of g of x at c is just the same as the uh, f of the limit of g of x at c. or simply f of L, or again, L is the limit of the inside function at C. Basically, this property says that when these two conditions are met, these two about the functions f and g, the passing of limit through a function becomes possible. Nice property. Let us look at this once again. So with the limit operation passes through f. Look at this. Very nice. So finding the limit of a function at the given point speeds up our computation big time, right? If we know this. For example, to find the limit of that one, the square root of x squared minus x plus 4 all over x plus 4 can be expressed as the composition of f and g, where g of x is a function equivalent to this inside function inside the radicals, while g of x is just the f of square root of x. So f of g of x becomes this. Alright, so since these two functions together with the c value satisfy the above conditions, the passing of limit inside the function f is warranted. Therefore, the computation of limit can be done this way. So the limit went inside the radical, and direct substitution is applied because this is now already a rational function. So direct substitution is applied, and so we get the final. So you can still simplify this, but this one is acceptable. So we are done with polynomials, and rational functions, and those that involve radicals. Now we will discuss the limit of transcendental functions. We will start with trigonometric functions. So it says that if C is a real number in the domain of the given trigonometric function, then I will not read this anymore. I will just say that direct substitution is allowed. If C is in the domain of the given trigonometric functions, all right, you simply directly substitute. Therefore, we might want to recall what is the domain of each of these trigonometric functions. Let us recall. So this is from your high school mathematics. For sine function, the domain is the set of all real numbers. Very nice. So under sine function, if we are taking limit of sine x, we simply substitute c in place of x, no matter what c is. For cosine, cosine has the same domain. So just like this, we can directly substitute when we're taking the limit at c. But for tangent, there are some restrictions. We can use direct substitution except when c is one of these. Pi over 2 plus the multiple of pi. Okay? We don't want this. If c is one of these, then we cannot use direct substitution. For secant x, the domain is the set of all real numbers except the same as that in tangent, meaning direct substitution is allowed as long as the number c is not one of the following. one of these. Say, for cosecant x, the domain is the set of all real numbers except a multiple of pi. Here, k is an integer. So, direct substitution is allowed as long as the c is not one of these. And the same is true for cotangent x because they have the same domain. So, it should not be one of these. All right? Are you still with me? All right. So, let us do some illustrations. The limit of sin x as x approaches 0. So we know that 0 is in the domain of sin x. So we can just do direct substitution. So the limit of sin x as x approaches 0 is just 0. Next, number 2, the limit of x times cosine x as x approaches pi. Here we can first use the multiplication property, knowing that the limit of x as x approaches pi exists and the limit of cosine x as x approaches pi also exists. So we separate them, and for this one we can refer to this list that pi is in the domain of cosine function, so we can use that direct substitution. So here it comes. All right, so this limit becomes just cosine pi. This limit becomes pi. And cosine pi is -1. So our final answer is negative pi. Very easy. Number 3. So the limit of tangent x as x approaches 3 pi over 2. If you remember the list, this was the list that we want to avoid if we are to use direct substitution. So is 3 pi over 2 in this list? But I think, let's see, 3 pi over 2 is there. So we cannot directly substitute. So what do we do? Well, we can resort to numerical approach of finding the limit. You can, you know, use tables, assign values for x from left and from the right, then compute for f of x. You know the drill, and you see the pattern, and what it will tell you when you do that process is that f of x will increase without bound, suggesting that the limit of tangent x at 3 pi over 2 does not exist. And that is in fact the case, that the limit of tangent x at x equals 3 pi over 2 is does not exist. All right. Next, number 4, the limit of sine 2x as x approaches pi over 2. This is a problem
Oh.
because our list of properties, this one, only contains the angle x, not 2x. This is angle 2x. This is angle x only. But we have a solution to that.
Really?
We can use the double angle identity of sine function to rewrite the limit as, so the sine 2x becomes 2 sine x cosine x. And now the angle is just x. So we can now use this. So first we can use the scalar property to get rid of the constant. Then we can use the multiplication property to separate this product. And yeah, that will get the job done. All right, so now we use direct substitution here. because pi over 2 is in the domain of sin x and cosine x. And simplifying that gives us 0, right? Very easy. But wait a minute. Can we use the property of the limit of composite function? Actually, we can,
Really?
since the condition it requires are met. When we go back to the assumptions under the limit of composite functions, this limit problem will satisfy that requirement. Therefore, we can use the limit of composition of function. How will the solution look like? Well, check this out. All right, so the limit operation gets inside the sine function. So when it is already inside, we're now dealing with the limit of 2x. And so we can use direct substitution. And in so doing, we get sine pi, which is equal to 0. Very nice. All right, so let us summarize the approaches we have so far employed to find the limit of a function from the beginning. First, we started investigating the limit using intuitive approaches. What are those? Numerical and graphical. And because we wanted to make sure that the answer we're getting from these approaches is correct, we compelled to test it using the very definition of limit. However, this process is kind of cumbersome, so we turned to solving limit of a function using analytical approach, and that involves using the applying the properties of limits, the list of verified and ready to use properties of limit. So we started with the basic limits, those two, and as that can only solve a very limited list of functions, we established the rules for all operations on functions, the addition, subtraction, multiplication, division, scalar multiplication, as well as exponentiation. But we are not contented with that. We have the limits of composite functions. But then again, we found it too tiring to carry out the steps by uh, the steps by step procedure in solving limit using this. So we ask, is it possible to just evaluate the function at C or simply use direct substitution? And fortunately, there are some functions. In fact, there are many of them. To name a few, we have polynomials, we have rational functions. There are some functions involving radicals, but with a little bit of restriction. And trigonometric functions also tells us that yes, you can directly substitute the c value as long as that c is in the domain of the trigonometric functions involved. All right, so that's the journey that we took when solving limit. We started with the intuitive approaches. We now proceed to analytical approach. Study tips. Number one, you must pay attention to the assumption of the theorems. For example, under multiplication property. So, as well as addition, subtraction, and division, the functions, the limit of functions has to have their limit exist already. We should know that their limit exists before we can use the rule. Right? Number two, when writing your solution, know when to omit the limit symbol. For example, this one, you have already substituted the c in place of x. And if you still use the write the limit, then this is a wrong notation. We should already remove of the limit, like this one, because you already substituted -2 in place of x. So yeah, that's it for today's lecture video. Thank you for watching.